So what we are discussing is about, if we take a bulk magnetic material, uh, so if we take a bulk magnetic material, normally it is in a multi-domain state, and what we get is like a hysteresis loop. But now if we decrease the size of that magnetic material, so what happens is it prefers to go into a single domain state. So it does not, so since the multi-domain state will have higher energy compared to a single domain state, so the energetically favorable state is a single domain state, which can be represented by something known as a super spin. Okay, that means since all the magnetic moments, the atomic magnetic moments are pointing in the same direction, so you can represent the whole cluster or your magnetic nanoparticle with a single spin, which we call as a super spin. Okay, and the question is, if in a multi-domain state we have a hysteresis loop, right? Then what will be the will there any change in the hysteresis loop or not? And we actually did a small calculation to show that that if you to compare the energies of different, like a multi-domain state and a single domain state for a spherical particle. Why it's not changing? Okay. Go back here. Okay. Yeah. So so if you compare the energies of a single domain and a multi-domain state for a spherical particle, so we see that there will be contribution that is known as a magnetostatic energy or the volume energy. Uh, and then you will also have contribution due to the domain wall as well. And one can calculate it using simple doing some simple calculations. Okay. So do you see the slide when yeah, okay. So it's somehow a little bit slow, lagging behind. Okay. Uh, so you can calculate the energies of the magnetostatic energy, as well as like, yeah, we just looked at this demagnetization factor. And so we'll just go through it quickly. And so you can calculate the energy, the magnetostatic energy, and which will be this much. Okay, so the volume energy basically for a sphere. And since you have a domain wall as well, so that will also cost some more energy. Okay, so due to the domain wall, and the domain wall energy is normally we write it as so if it is a 180-degree domain wall, or so if it is a 180-degree domain wall, have a domain wall energy given by this much. And so you can compare the energies of a single domain state and a multi-domain state. Okay. And you can arrive at a critical radius RC. Okay, so which one can calculate, and that means it is possible that for certain critical radius RC, uh, or at at a critical radius r or a critical dimension, your particle will prefer, or your magnetic material nanoparticle will prefer to stay in a single domain state compared to a multi-domain state. So when you look at the how the coercivity that actually varies as a function of the particle size, so what you observe is like it initially uh, increases, and then at a critical dimension or the size of a particle, so you make a transition from a multi-domain state to a single domain state, and then again the coercivity is decreasing, and then for very small tiny particles it happens that the coercivity actually becomes zero, and that is the region where the particle, this magnetic particle, nanoparticle, is supposed to go into a super paramagnetic region. And if you look at the coercivity, so you see a large coercivity or a hysteresis actually in single domain as well as in multi-domain case, but there is no hysteresis as such in case of a super paramagnetic particle. But what is interesting about this super paramagnetic particle? So of course they are ferromagnetic in a sense. They are in a single domain state, and they have very high saturation magnetization. Okay, so ms is about 1,000 mu Bohr. So like if you take think like you have a cluster which has 1,000 atoms or 5,000 or 10,000 atoms, and each atom is contributing a 1 mu Bohr magnetic moment. So then you can imagine it could be like 5,000 mu Bohr of magnetic moment. So the total, the super spin magnetic moment ms is quite high. Uh, but in this small cluster size, what happens that this magnetic moment is not really stable, but it fluctuates due to the temperature, and due to this fluctuation, so it is almost like similar to like a super paramagnetic or paramagnetic, so it behaves like a paramagnet. So that means the magnetization fluctuates with temperature, and you basically appears that there is no magnetization at all. So when you take a average over time or over space, so you observe that the total magnetization is zero due to the thermal fluctuation, very similar to a paramagnetic case. But here we call it a super paramagnet because the magnetization is very huge. So in a paramagnetic case, the spins which are fluctuating, the undergoing the thermal fluctuation, are typically maybe again 1 mu Bohr or few mu Bohr. Okay. So if we are talking about electrons, so of course, so like 1 mu Bohr, that is the magnetic moment, and that is the typical uh, magnetization that is fluctuating due to the temperature, your thermal energy. But here you have this huge magnetic moment which is fluctuating, and that is why it is called super paramagnet. So again, so this picture shows here the same behavior, that how coercivity is changing as a nanoparticle radius. Okay, so you have a lots of domains, multi-domains in a bulk material, but as you decrease the size, so you decrease the number of domains, also decrease the number of domain walls. But again, at a critical point, you enter into the single domain state, and then this single domain state remains. It does not change to any other kind of things. But additionally, what happens when you go to very small particle size, so you enter into the super paramagnetic regime, so which is this regime. Okay. So these are few electron microscope images of a magnetite nanocrystal. So this is a kind of it's a super paramagnetic particle. So people have synthesized like all kinds of shapes and dimensions, and then you can also assemble it into larger dimensions. So they can sell. So the top images are basically your and and the bottom images are basically when they self assemble into different structures, so you can get this I'll just again share the screen. Okay. Yeah, so you have uh, you can synthesize in different shapes, okay? So cubic or spherical or like some complex geometrical structures, and then when they self-assemble, so you can get so the dominant uh, term here or energy, the interaction is your magnetic dipolar interaction that could lead to this kind of long chains, formation of long chains of magnetic crystal. So these are also again some, we have more examples of different magnetic, so spherical, these are spherical, almost spherical nanoparticles. Okay, so very good size distribution. And you also see here these are the your high resolution TEM images, okay, where in fact you can see really clearly the that these individual nanoparticles are actually crystalline in nature. They are really highly crystalline. Okay, so and they are in fact in a single domain state. Yeah, so to describe, so in a typical magnetic cluster, what you have is a hysteresis, or you have a, so that means how the magnetization varies as a function of field, and then how the magnetization varies as a function of temperature. Okay, so these are the two things which are normally, that is you are interested in terms of their magnetic properties, how they vary with magnetic field and how they vary with the temperature. So there are two models to describe that. So the first, the Stoner-Wolfach model, it describes how the magnetization varies as a function of field. So, so this is again a like a approximation we have done here. So we have taken a like a almost ellipsoidal particle, and we assume that the magnetization, this is your M and P, and H is your external field, and this K is known as your anisotropy uh, constant, or this is the axis of your anisotropy. So along this direction, so along the k direction, so you have the anisotropy. So what is this anisotropy? So anisotropy is basically, it is like a, so normally it is called as also a magnetocrystalline anisotropy. Okay, so this is also known as crystalline anisotropy as well. So basically it defines like a easy and hard axis magnetization. So it defines a, basically the direction of your anisotropy is known as your EG axis. That means your magnetization prefers to stay along that axis, that anisotropy axis. So if you have a magnetic system and you have a magnetic anisotropy inherently will be there due to the crystalline structure, and magnetization would prefer to stay along certain crystallographic directions, and that those directions are known as EG axis, and your anisotropy will be along that EG axis. So that means if you do not apply any magnetic field, so the magnetization would prefer to stay along that direction. So it can be, and mostly it is along certain crystallographic axis. And similarly, the direction which is 90-degree to it, so which is perpendicular to it, will be known as a hard axis. Okay, so you will have a EG axis and you will have a hard axis. So here in this picture, so let me, yeah, so this is, let's say, a cubic structure you have. Okay, so what you have is different crystallographic directions, right? So let's say your 100, this is your 100 axis or 100 direction. Then you'll also have a 111 or 110 direction. Then you also have a 111 direction. So different crystallographic directions that can exist in a cubic crystal. Okay, and so all these directions will have, so the magnetization, so depending on how the crystal structure is, so magnetization actually prefers to stay along one of these crystallographic axes, along one of these directions. So here in this you see a this is an experimental measurement of magnetization as a function of field of a single crystalline iron. Uh, so it is an iron crystal, single crystal, and they measured the magnetization as a function of magnetic field H along different crystallographic axes. So what, from this figure what you see is along 100, it is easy to magnetize or saturate the crystal. So if you apply the magnetic field along the 100 axis, so you can easily magnetize it. So you can easily saturate it. Okay. So saturation means, so that's this point will be your saturation point. Okay. So where magnetization is, it is not changing anymore. So that means your material is saturated. So you got a highest ms value. So what you see here is this, to get to saturation along 100, so you apply a small field H1. But now if you are applying the field along 110 or 111 direction, so you have to go to probably quite high value H2. So here your H2 is greater than your H1. Okay, so that means you have to apply a very high field to saturate it along other directions. So therefore this 100 axis is, for iron, is known as a EG axis, or that is the direction of your anisotropy axis. and the other directions are normally, you can call it a hard axis or semi hard axis, and so on. So similarly, this is an example of cobalt. In case of cobalt, what you see is your 111 axis is actually an easy axis, because the magnetization can be easily saturated when you apply a field along 111 direction. But 100 and 110 are actually the hard axis. So your crystalline anisotropy, magnetocrystalline anisotropy will tend to align your magnetization of your crystal along 111 axis in cobalt, but in iron it will be along 100 axis. So that means it always will cost certain amount of energy if your magnetization deviates from your anisotropy axis, because the preferred orientation of magnetization is along the anisotropy axis. But now if for some reason your magnetization deviates a little bit, so this is a vector quantity, so if it deviates a little bit from your anisotropy axis, so it will cost certain energy, and that energy is normally, we call it the anisotropy energy. Okay, so this is your anisotropy energy, kv into sine square phi, so where phi is your angle between your magnetization and your anisotropy axis. Okay, so that means the what will be the minimum energy configuration for a magnetization. So if phi is equal to 0 or equal to pi, so then the energy is normally minimum. Oh, sorry, it will be 0 actually, right? Because sine 0 will be 0. Okay, so energy will be minimum. So instead of this kV, it will be, E will be equal to 0, right? So that means there will be no extra energy or magnetic energy that will be introduced into the system if the magnetization is along the k axis, along the direction of your anisotropy. But if there is a simple deviation, so your energy will be given by this formula kv sine square phi. And then if you have external field H, okay, so then you also have a Zeeman energy, right? So this magnetostatic energy, which is given by this mu naught H dot M, and this V is your volume. So this is your Zeeman energy due to the external field. And these are the basic energies which are actually involved when you want to investigate or model how magnetization varies as a function of field. So you have basically two energy terms here. That is what we have, this slide shows. So you have phi is the angle between M and your anisotropy axis, so which is given by kv sine square phi, and this is your G-man energy, because the G-man energy is between your magnetization M and the external field H, and the angle is theta minus phi. Okay, so from this figure, so this is your G-man energy, and so you can actually minimize these energies. So you can take as a function of phi, so what will be the equilibrium configuration for M, so that the energy will be minimized. So you can take dE by d theta or d phi equal to 0, and then you can calculate. So by analytic calculation, so let's say you can find out what will be the equilibrium, the best, the minimum energy configuration in this situation. So you have K and H, which are basically two uh, vectors, and magnetization. So that means if the magnetic field is high, so then magnetization this will prefer to lie along the field direction. That means the angle phi will increase more and more. So of course it will increase the anisotropy energy, but then there is a balance, whichever wins, so that will decide whether the magnetization will be along the k axis or will be along the h axis or something in between, some resultant direction. Okay, so one can actually draw this magnetization as a function of field for different angle phi. Okay, so we can draw that. So this is when your angle phi is equal to 0. So that means the magnetization is along the k axis, or let's say if there is no external field H is applied, so the phi will be equal to 0 and your magnetization will be almost like a square loop. So it is a perfect square loop. But if phi is 90-degree, so what you have is this kind of, when phi is equal to 90-degree, or let me write it down, phi is 90-degree, so you get the red color curve. So that means you actually observe no cohesivity here, and that means you are measuring the magnetization along the hard direction. So in any typical ferromagnetic material, when you want to measure the magnetization as a function of field, so if it is a single crystalline, this is what you'll get. So something which will be in between, you will get probably like something in between will be like this. This is what you typically observe or obtain in many magnetic material, and that means your that shows that your there is actually a distribution of anisotropy axis. So for some, so when you are applying a magnetic field in a polycrystalline material, so for some crystallites, the magnetization or the EG axis will be I mean, the magnetic field will be along the EG axis. For some, it will be along the hard axis. So you get an average kind of picture, and this is what you get. Okay, so this gives you idea about the magnetization, how a single domain magnetic cluster will behave in presence of a magnetic field. But what is interesting also is how it behaves in a presence of temperature. So, uh, So one is this Stoner-Wolfert model, and the other is known as, actually the term is known as this Neil Brown model. Okay. So where what we are saying is that, so what we observe, let's say if we say if we have a single domain particle, so we have two energy terms or two different anisotropy directions. So one is the EG axis, one is the hard axis. So your superspin, this large magnetic moment, the magnetization prefers to stay along the EG axis, either, so it could be theta or phi can be equal to 0 or pi. That will give rise to a minimum energy, right? So this is what is represented here when you are plotting energy as a function of your angle phi. Now, if the angle phi is 90-degree, so I will have the energy will be k into v, because sine square phi will be equal to 1. So the energy will be kv. So that means I have a configuration. So it is like two possible configuration, minimum energy configuration. So theta of phi equal to 0 or pi, which is separated by a energy barrier delta E, which is equal to K into V. Okay, so this is your energy barrier. But now, if your thermal energy is high enough, okay, so if kt, this value of kt is high enough or compared to your kv, your delta E, so if your delta E is of the order of your kbt, so in that case what can happen, there can be a fluctuation, this so your magnetization can overcome this barrier. So due to the thermal energy, it can fluctuate between these two valleys. Okay, so this is, both are possible. Okay, both are stable configuration, but since you have a thermal energy kBt which can overcome this barrier, so there can be a jump from one configuration to other configuration, and that is what basically leads to your thermal fluctuation. So now why it becomes important when you go to a smaller size, because again, so one has to look at what is uh, the temperature or this thermal energy, and what is the energy barrier. So that means the energy barrier, as you can see here, has a term V, volume, right? So that means if you go to smaller volume, so this delta E, the barrier will decrease, and therefore the thermal energy will be enough to overcome this barrier, and therefore your magnetization will fluctuate just like a paramagnetic case, and that is what gives rise to a zero coercivity or this super paramagnetic fluctuations. And normally this is expressed in, sorry, uh, normally it is expressed in this thermal like a Arrhenius like expression. So this is your time scale of fluctuation tau. Okay, so time scale of fluctuation tau will be tau naught into exponential kv by kVt, so delta E by kBt. So that is your fluctuation term, so you can also convert it in terms of frequency as well. And uh, and this model is uh, known as your Neil Brown model. Okay, I mean, so there are two possibilities here. Okay, so when this fluctuation normally, so when people talk about these fluctuations, so one is like your all these spins inside your nanoparticle. So these tiny spins, magnetic spins, so they will rotate coherently. Okay, so just at a exactly some certain time, suddenly all will flip. Okay, so let's say in the beginning, so they are in theta equal to 0 situation. Okay, so they are in a theta equal to phi equal to 0 position, and then at certain time, so due to the thermal energy, they will all will flip and go to theta equal to phi, phi equal to pi. So they will flip. So that is normally known as a nail model. So sometimes it also happens, uh, this is also a possibility that a particle, so let's say we have a particle in a fluid or in a solvent or in a solution. So what can happen, so this magnetization axis, so let's say it is pointing along certain direction, and then the whole particle will rotate. It is like a mechanical rotation of the particle, and then the magnetization will go to the angle pi. So it is, let's say, along certain direction. Of course, it is random, one of the particles. So you can think in a liquid, like in a solvent. So you have lots of number of these particles. So what can happen is this particle is there and pointing the magnetization. Let's say it's pointing along some direction, but due to the fluctuation, so the whole particle will rotate. So it is like a mechanical complete rotation of the particle itself that leads to a fluctuation from or configuration from phi equal to 0 to phi equal to pi. Okay, so this is also a possibility. This is how this thermal fluctuation can happen. Okay, so it is very similar to like a Brownian motion, you can say, but although Brownian motion is completely random, but here the rotation is such that, so the magnetization is either along the 0 or will be along the will be making an angle pi with respect to the initial orientation. So both are possible ways how this thermal fluctuation can take place. So so we'll not go into the detail of these equations and so on, but one can actually find out some characteristic temperature which defines like or differentiates uh, between a super paramagnetic particle, whether like what is like how this transition happens in a super paramagnetic particle. So the thermal fluctuation, will it occur for the entire temperature range, or is there like something like a some temperature range where the thermal fluctuation will be there, and for some temperature range it may not be there? Because again, as we saw that this kbt, this delta E, okay, so your delta E should be of the order of kBT. Okay, and this delta E, this barrier will change as a function of temperature. Oh, sorry. So the barrier is always fixed, but this kBT will change as a function of temperature. So that means it is possible that for certain temperature you can have fluctuation, and for certain temperature they may not fluctuate. And this is typically distinguished or differentiated by this uh, term blocking temperature. So TB, okay, so this is known as a blocking temperature. And but let's say without really going into the details of this, so I'll just show here one example here. Hopefully, yeah. So what you have is here, like what we are measuring is a magnetization as a function of temperature, okay. And then as you see here, oh sorry, so we are measuring as a function of temperature, okay. So what we see here is no, come on, that at a particular temperature TB here, for a particular temperature, blocking temperature, so above this blocking temperature it behaves, so there is thermal fluctuation, but below the blocking temperature, so the magnetization will freeze into one configuration. Either it will be frozen into theta equal to 0, or I mean phi equal to 0, or phi equal to pi configuration. One of the configuration, it can be frozen in one of the orientation. And then once you go above this TB, this blocking temperature, so that is why it is called a blocking temperature. So that means the fluctuation will be blocked below this temperature, and then a fluctuation is possible above this temperature. And but in both cases it is a super paramagnetic particle. So this is like a typical measurement that is done, this GFC. It's called a zero field cooling and field cooling measurement. I mean, we don't need to go into the details of that, but this is basically a standard, like a experiment that is done, normally done to understand the behavior of super paramagnetic particles. But remember, this blocking temperature is not like a Curie temperature. Okay, so you also have a Curie temperature, which is uh, kind of like a gives rise to a phase transition. So you have a paramagnetic to a ferromagnetic phase transition at a Curie temperature, and that Curie temperature is normally uh, like fixed. Okay, and normally there you will not observe really a size dependent of Curie temperature, and but this blocking temperature is not like a phase transition. So we are not going from a super paramagnetic to any other non-magnetic system. It is always in a ferromagnetic system. Only what is happening, that there is a transition on the transition from a frozen or a blocked state to a unblocked fluctuation state. Okay, so that is what is happening. So it is not really like a phase transition. So one has to be careful about that. Uh, yeah, this picture here basically shows that what I told here. So let's say below TB, So below TB, so you have this is in a blocked state, and then when you go above TB, this blocking temperature, so they are in a fluctuating state, and then when you go above TC, so again they will go into a paramagnetic state. So in this between TC and TB, so they are still in a ferromagnetic state, but they are fluctuating. Okay. Uh, and therefore one can also observe, so sometimes you will observe a hysteresis, so if you go below the blocking temperature, so if you make, so because they almost behave, they are in a frozen state, so they behave almost like a ferromagnetic material, and you will actually observe a hysteresis below blocking temperature. But between blocking temperature and TC, so you will not observe a hysteresis. Okay, so the cohesivity will be zero. But of course if you go above TC, as always for all magnetic material, it will behave like a paramagnet. So the applications are basically mostly right now that is being used in drug delivery, mostly for biomedical applications. Okay, because I mean super paramagnetism is actually kind of a bad thing for magnetic storage. So if you think about it, so if you want to increase the magnetic storage density of your hard disk, it is not good. Because the thermal fluctuation will lead to destruction, or it will destroy how you store your information. uh, but it has other advantages mostly in biomedical applications. So most likely I think we will discuss in the third fractal when we go to the third fractal. Okay, so this is for today, and we'll stop now, and then I will actually I will send. So there are lot of other clusters or magnetic, not magnetic, other kinds of clusters that can exist. So I will share this slide today with you. You go through that, and maybe we can start with a discussion tomorrow on this what I will share today. Okay, what is the temperature range for between TB and TC in terms of value? That again depends on the size, the blocking temperature, the value of blocking temperature. Again, I did not want to go into that. Actually, the blocking temperature, the value, it depends on pretty much how you measure it. So what is your measuring instrument? So for example, here I mentioned this squid on the left side, you can see that is a typical magnetometer that is used to measure magnetization. So if you measure in squid, so you'll observe a TB, so this is measured in squid for example, and you typically observe a about 20 Kelvin or 15 Kelvin, but of course it depends on the size as well. So the blocking temperature can also vary, but it also will vary for the same material. So if I take, let's say, a 20 nanometer iron particle, okay, and I observe a blocking temperature at probably maybe 40 Kelvin, using squid. But if I do another measurement, so if I measure it another magnetometer, or so a different magnetometer, okay, so let's say I measure it in a or so there are different ways to measure the magnetic moments. So I can do it in a NMR technique, or let's say I can do a neutron diffraction. I can also measure the magnetic moment. uh, so if I take another experiment altogether, in that case, the blocking temperature can be also different. Okay, uh, and why? This is because, oh, sorry, this time scale of fluctuation. Okay, so this tau, it depends on the experimental time scale. Okay, so whether the system is in a blocked state or a unblocked state, so that depends on the my measurement time. Okay, so if my measurement time is different, so if I am measuring for, so let's say my fluctuation time is 5 seconds. Okay, So now, and I am measuring it. My instrument measures the magnetic moment, gives an average over 10 seconds. Okay. So now, when I am measuring in 10 seconds time scale, if the fluctuation is 5 seconds, so that means I can observe the fluctuation. Okay. Now, if my instrument's measurement time is 1 second, okay, so now I have the particle and I measure the magnetic moment in 1 second I measure. But the particle takes 5 seconds to fluctuate. So that means in that device, that instrument, my fluctuation has not happened for the particle. Okay, so this is a very crucial or very delicate thing. So it depends on in which what is the technique that you are using to measure this blocking temperature. So for the same iron 20 nanometer particle, if the fluctuation time is 5 seconds and I am measuring in device 1 with a 1 second resolution, so I'll say, okay, in 1 second I do not see any fluctuation. So I would say, okay, probably this is in a frozen state. But if I measure for 10 seconds in another device, I would say, oh, okay, so blocking temperature maybe in that case will be higher. Okay, so this is uh, depends on the measuring instrument. Okay. Okay, so if you have questions, we can take it tomorrow. So we'll stop for today, and I will share the whole slide. So there are other like semiconductor particles, also some other concepts that are there. So we can start with a discussion on that tomorrow morning.
Sir, the books you shared also consists this part also, this super paramagnetism part.
Super paramagnetism, not really. So these are actually taken from some other material. So it is not from one book. Let me, I mean, because, so I can share, actually, this is taken from one review paper. So I will share that review paper so you can go through that. That is
Okay,
also a
sure,
nice
sir.
review paper. I will share
Thank you,
that.
sir.
Okay.
Thank you.
Yeah. Okay. Okay. So thank you. So we'll stop.